All right, so this began, if you remember last time we were talking about, we'd moved into ketones and aldehydes, and we had talked about their nomenclature and talked about their preparation. And we had seen that a number of the ways of preparing aldehydes, for example, were review. And then we started talking about ketones, and it was the same thing. And we finished class last time where I had listed the review examples of how to prepare ketones. And that was going to leave us then to begin today with a new reaction that forms ketones. And I kind of did foreshadowing last time, and that is it's a reaction that actually comes from acid chlorides. And it uses basically a partial, what we would call a partial alkylation. Because we know normally if you took an acid chloride and reacted it with something like a Grignard reagent, which is an R nucleophile, which is what we would need here to convert an acid chloride into a ketone, right? We would need an R group to substitute for the Cl, and then we'd end up with a ketone. Well, Grignards we've already looked at. They react twice with an acid chloride, two equivalents, and they end up giving the alcohol. So we need some carbon nucleophile that is less reactive, that will only react once and give us the substitution and not the addition product. Okay, and so we need something that does this type of reaction where we have our acid chloride and we're going to react it with an R nucleophile, and we want it to just end, and I'm going to put a prime on this R so we can identify what's happened is, the chlorine is in the box here as a leaving group, and so my R group is basically substituting for that, and then the reaction stops. There's not a second equivalent of R minus that reacts, because that would give us the overall addition in the alcohol. We want it to stop with the partial alkylation at that step, and that would give us then the ketone. Okay, so for the reasons we just explained, it can't be the Grignard that does that. So it's actually our friend the Gilman reagent that we looked at earlier, which is that copper lithium reagent. Okay, so in the beauty of digital technology, I can erase this because I know you can always pause it to write all of that down. And so do you remember what the Gilman was? The Gilman was that reagent where we effectively reacted an alkyl halide with lithium and then with copper, and we ended up with this reagent that is a copper lithium reagent where we have two R groups attached, and I don't want that to look like a G, it's a copper. And so the reactive equivalency of this is just one of these R groups has the reactive equivalency of R minus. So even though there are two R groups on here, a Gilman is still just delivering one alkyl group. Okay, and so if you want an example of that, and this would be something, the reagents on this arrow are going to be what you would have on your flashcard. Let's say that we have this acid chloride, and I'm going to react it with the Gilman reagent, and I'm going to use a dimethyl Gilman. Okay, so I have the two R groups and they're methyls, so remember the reactive equivalency of that is that it's one methyl, and since it's not as reactive, okay, as a Grignard, it's only going to do the one equivalent reacting, so that's actually ending up being a substitution reaction and not an addition, so you stop at that point right there. And so this is a new way of making ketones. Now notice that, we have the Grignard that gives one reaction, and now the Gilman that gives a different one on an acid chloride. So they're both organometallic reagents. They're both R nucleophiles, but they have different reactivities. All right? And so that's not the only new way we can prepare a ketone. We can also do it from nitriles. And we will see the nitriles are kind of going to be included eventually in our category of carbonyl compounds, even though it doesn't have a C double bond O, because nitriles react in a very similar way to a carbonyl. And so we can take a nitrile like this, and we can react it with a Grignard. And I'm just going to use R prime. And remember, Grignards were our magnesium organometallic, and so it's a reactive equivalent of R minus, whatever that R minus is. And so that can act as a nucleophile, and it's going to react with the electrophilic center of the nitrile, which is this carbon, which breaks this pi bond and moves the electrons out to the nitrogen. So you can see how this is kind of similar to what you would see with a carbonyl compound. And the result of that then is that you have now added whatever that Grignard alkyl group was, you've added it to this carbon. This R group is still here. You've broken one of your pi bonds, and it's actually the magnesium bromide that's associating with the nitrogen, because that nitrogen got a minus charge and was able to associate with the magnesium. So you get this intermediate, which is then worked up. I'm going to bring the arrow down here. It's worked up just like you normally do with a Grignard, aqueous acid, right? And if you do that, you end up forming the ketone plus NH4 plus. Okay? The only important thing we're going to look at with this reaction is that your nitrile reacting with a Grignard gives the ketone. We're not even going to worry about the mechanism here. Okay? So just know that that is a way of preparing them. And if you want an example that doesn't just have R's, let's look at what it would look like on an exam if you were preparing this from a nitrile. And let's say that we just had this nitrile, and we're going to react it with a methyl Grignard, okay, followed by the aqueous acid workup. So that's what your flashcard would have, these reagents. What's typical for a Grignard reaction. What's different is it's on a nitrile, and the result of that is going to be the formation of the ketone. And whatever this R group is, from the Grignard is what's going to be on that side of the ketone. So, if you change this R group, you're changing that position. But a very good way of making ketones. All right, so that concludes ways to prepare aldehydes and ketones. So we want to work our way into reactions of aldehydes and ketones. But before we get into the most common reaction they undergo, I just want to briefly mention oxidation of aldehydes and ketones. And this is only going to take this one little dry board, because it's not a major reaction that we do, especially on ketones. But before we get to the meat of the reactions, I want to just mention that you can oxidize aldehydes and ketones. Okay, and so we have now transitioned into reactions of aldehydes and ketones. All right, so the first thing is aldehydes. And aldehydes, we already have looked at this. We already know they can be oxidized. Remember, we looked at primary alcohols could be oxidized either to the aldehyde or the carboxylic acid, depending on what oxidizing agent you used. Do you remember? If not, go back and review that, because there's a difference between PCC giving the oxidation to the next oxidation state, so primary alcohol to aldehyde, but then we had to use Jones's reagent to oxidize it all the way up to the carboxylic acid. But you can start at the middle point. So for example, if you already have your aldehyde, you can oxidize it. You can't oxidize it with PCC, because remember, PCC only oxidized a primary alcohol to the aldehyde. It didn't oxidize it further. So you would have to use Jones's reagent. And if you use Jones's reagent, then you would oxidize that aldehyde to the next oxidation state, which is the carboxylic acid. So this isn't really a new reaction. We're just looking at the first oxidation state to the second oxidation state of a primary alcohol. All right, but it is a way of taking an aldehyde to a carboxylic acid. Now, if you remember, when we talked about ketones, we actually said that ketones cannot be oxidized. And in the context of what we were discussing earlier, that is absolutely true. But you can actually oxidize a ketone, but you're not going to oxidize it in the same way. It's actually going to be an oxidative cleavage reaction. Because remember, the problem was you didn't have enough, valency, or I'm sorry, you didn't have the proton you needed to do the elimination to go from the alcohol to the ketone. And so when you got to a ketone, you couldn't oxidize any further. Okay, but you can do an oxidative cleavage, and that's where you take potassium permanganate, which we know as an oxidative cleavage reagent, and you do an aqueous acid workup. And when you do that, you actually cleave this open. Okay, so there's no way to oxidize this, directly to a carboxylic acid, keeping this ring, intact. It has to be cleaved open to allow the valency you need. And so you end up forming this dicarboxylic acid. Now, this reaction is rarely used. I don't think I've ever used it in a synthesis problem or anything else, but just so you know, this is a possible reaction. But the only way you can oxidize this is to actually do a cleavage. All right? So that brings us to the most important set of reactions. Nucleophilic addition. Now remember, when we did our general carbonyl overview, what we said is, there were those 4 types of reactions we talked about. We said the 2 types that are most important are nucleophilic addition and nucleophilic substitution. And we said that aldehydes and ketones underwent nucleophilic addition. So we've already looked in a general sense at what the mechanism of this is, okay, and what the results are. So now we're going to start looking at it very specifically, okay? And remember, there were 2 types of mechanisms that could occur with a nucleophilic addition reaction, and it depended on whether the nucleophile was neutral or negatively charged. So the first thing we want to do is we want to talk about what nucleophiles there are that can add to a ketone or an aldehyde. And so we can have negative ones, and we can have neutral ones. Okay, and remember, one of them was a straightforward addition that always gave alcohols. And then one was where you added the nucleophile and then you expelled water. And so you got a little different result. And basically, you can see neutral addition of nucleophiles with water, with alcohol, and then with, amines, and you can, I'll just draw all the different kinds of amines. These we don't really talk about. And so as far as the neutral nucleophile goes, we're really mainly talking about amines, okay? Because they are nucleophilic enough to react as is. But under the negative category, we can talk about hydroxide, hydride, which is something that we've already looked at. We can have carbon nucleophiles, which are going to be like Grignards or Gilmans, and OR, your alkoxy, and CN minus. All of these are negative nucleophiles that do very straightforward addition reactions on ketones and aldehydes. So these are the kinds of things we're going to look at, and we're going to take them one by one. And each time we look at a reaction of one of these nucleophiles with the ketone or the aldehyde, we have to ask ourselves a couple questions. And so when you're doing a nucleophilic addition, there are two important factors. Okay? The first is the reaction reversible? Okay? Will the nucleophile go on and then come back off? And just, because I know you probably listened to these a couple times, I can say, a nucleophile that is also a good leaving group is going to be something that would be reversible. If your nucleophile is something that's not a good leaving group, then when it adds, it's not coming back off. And so it's actually reasonably easy to answer this question. And the second one is it acid or base catalyzed? Because these reactions typically require either base or acid to catalyze them. Okay? And so each time we look at a reaction, we're going to ask ourselves these questions, or I'll rely on you to ask yourself the question about them. Okay? But before we get into the actual reactions, there's one simple thing that we should talk about in terms of reactivity. And that is a simple question: which is more reactive? Aldehydes? Ketones? Which do you think is more reactive? And how would you figure that out? Well, there are actually two ways to look at this. Okay? And it turns out that aldehydes are more reactive. But there are two explanations. One of them, if y'all were actually sitting out there, all I'm looking at now is my vacuum cleaner that's sitting right there. But if y'all were out in the class and I asked you this question, why do you think an aldehyde is more reactive, what would be probably your first answer? It would, a lot of times that we ask about reactivity, it has to do with sterics, right? And so sterics is one of those explanations, because basically we have a situation where you have an aldehyde versus a ketone. And if you're thinking about a nucleophile needing to add into this electrophilic center, and you're comparing structurally an aldehyde versus a ketone, this has an H attached, this has an R in that place. So here you're basically talking about what might be equivalent to secondary versus tertiary center, like if you were talking about substitution reactions. Therefore, this less steric hindrance to the attack of the nucleophile. So that makes this more reactive in terms of sterics. And that's the one that's a little simpler. Okay. What could the other explanation be? It has to do with electronics. And that's when you're thinking about the reactivity. Right? You're thinking about the fact that in each of these structural cases, the carbonyl carbon has a partial positive charge. Okay? So you can also think about these in terms of a minor resonance contributor. We've looked at this before because it kind of explains the reactivity of carbonyls. If you look at this resonance form, where you actually have a pronounced positive charge at that carbonyl carbon, and I'm sorry, I need to put my H there. And so here you basically have this carbocation only has one R group attached. This one has two. So which of these carbocations is more stable? This one is. So that means that this is more stable than this. And if this ketone is more stable, then that means the starting material of the reaction is more stable. And anytime the starting material of a reaction is more stable, because here we're not talking about intermediates, we're talking about the electronics of that starting material. If you were looking at your energy versus reaction progress, this is ketone and this is aldehyde. Now, don't get confused if you need to review this, because we're not talking about carbocation intermediates in a reaction. We were talking about the resonance form for the starting material. And so that means we're talking about energy levels of these starting materials. Nothing to do with intermediates. We're still here at the aldehyde or ketone. So when I say that this minor resonance form of the starting material looks like this and is more stable, it hasn't reacted with anything yet. That's just a resonance form contributing to the ketone. You could also think about it as just this partial positive charge is more substituted, therefore more stable. So that means that energy level of the ketone is at a lower level. So if it's undergoing a reaction, okay, and going through a reasonably similar transition state, ketone less reactive because it's more stable. Okay. So now that we know that, it really all that matters is if you're trying to do a reaction, you have both a ketone and an aldehyde presence in your reaction, make sure the aldehyde is going to be more reactive. Okay, so let's start talking about the actual reactions now. So this is going to be nucleophilic addition reactions of aldehydes and ketones. And we're going to start with hydration, which is water. And I'm going to warn you right now that we're going to look at this because it's just a very classic example that explains a lot of things for us. It's going to explain the reversibility, and it's going to explain the acid-base catalysis. But the reaction of water with an aldehyde or ketone is a bad reaction. Okay? But mechanistically, it's going to teach us something, and that's why we're going through it. So if you're reacting water with an aldehyde or ketone, it's just a hydration reaction. Okay? And so let's start by looking at what would happen if you had a ketone like this, and we're going to react it with water. So here's my ketone, here is my nucleophile. Reaction occurs. It's an addition reaction. And so you're going to form this product. Because remember, when you have a ketone or aldehyde and you're adding a nucleophile, and let's just call that the one that you've added, then you're forming an alcohol. But here you're adding an OH, so you have another alcohol functionality. And so this is actually a gem diol. Remember, we've used these terms before. Diol because it has two hydroxy groups, and gem because it's geminal. Geminal, the two groups are on the same carbon. Vicinal would be if they were adjacent. Gem on the same carbon. Okay? Now, looking at that, the first question, remember, we ask is this reaction reversible? Well, I've actually given that away with the arrows, right? But if it's water that's adding, that water can come right back off because we know that water is a good leaving group. And so therefore, yes, this reaction is freely reversible. Okay? And in fact, it's reversible to the sense that it's 99.5% at equilibrium is going to be in the keto form. And so that's why I said this reaction really doesn't work well. Okay? But it does teach us something mechanistically. Okay? The only way you can get this reaction to go with any successful percent yield is if you use something really reactive like this. This is called formaldehyde. All of you have heard of that, right? And formaldehyde, when you react it with water, actually forms this gem diol. and it's about 99% in the hydrated form. And that's why if you ever find an old bottle of formaldehyde, it ain't this formaldehyde, it's the hydrated formaldehyde, because that reaction does actually favor the gem diol. Okay, and so Dr. Shedler, you're going crazy. Why are we going to talk about this reaction that really doesn't work well? Again, because it's going to teach us something about the catalysis that occurs. Because when you do this reaction, you can imagine it being base catalyzed or acid catalyzed. And it's going to teach us mechanistically, in a very straightforward way, what acid and base catalysis is going to mean with all of the other nucleophiles. Okay? And the reason that we use water to demonstrate that is with the same nucleophile, we can show what it would look like base or acid catalyzed because of that kind of dual nature of water. None of the other nucleophiles I can demonstrate both acid and base with the same nucleophile. So we're using this really as a model to explain catalysis. So if we have a base catalyzed reaction of water with my ketone, okay, if you're in a base, so you're base catalyzed, water is going to exist right as OH minus. That's the basic form of water. And so if that's the case, this is my nucleophile. A negatively charged nucleophile is going to react with the electrophilic center of the carbon. It's going to break this pi bond, move the electrons up to the O, forming the tetrahedral intermediate. Remember, we're going to see that a lot. And I'm just going to draw it like this. We're going to see that tetrahedral intermediate a lot. And so maybe the best way of showing it is to actually put in three-dimensionality, because we basically remember sp2 hybridized carbon to sp3. We're forming a tetrahedral intermediate. Every nucleophilic addition reaction and every nucleophilic substitution reaction, when we get to that, is going to go through the same darn tetrahedral intermediate. So this first step, we're going to see in all the mechanisms, okay? And so that's what forms. And then that's going to still have, you know, you're in water, right? And so this OH minus, the O minus is going to take a proton off of water, and so it gets protonated. That's going to give you this gem diol, but it's also done what? It's generated an OH minus. So all you have to do is really have one molecule of OH minus present. It'll do this reaction, and then the resulting O minus of the carbonyl gets protonated with water, and you reform your OH minus. So anytime that you have a nucleophilic addition that's base catalyzed, okay, what that's going to do is it's going to make this species more nucleophilic. It basically takes your nucleophile, makes it even more basic, because the base is going to pull a proton off of whatever your nucleophile is, making it more nucleophilic. So it's catalyzing the reaction by making the nucleophile more nucleophilic. That's how base catalysis works. Okay? But what happens if we use acid catalyzed reaction? Again, we're going to use water as our example because all I'm doing is illustrating this. So now it's going to be the acid catalyzed. And when you're acid catalyzed, I'm going to, again, I wish it wasn't a vacuum cleaner looking at me. If you're in acid, an aqueous acid, you have H3O+, right? And what happens when you put that in the presence of a carbonyl? The first thing that's going to happen is you're going to protonate that carbonyl, which is going to leave you with water. Okay? And once that occurs, then it's the water as a neutral nucleophile that's going to come in and react with the electrophilic carbon of the carbonyl, breaking the pi bond, moving the electrons out to the O, giving the tetrahedral intermediate, which would look like this. Now it doesn't have an O minus because it's already been protonated, right? And so then I have my two methyl groups attached, and then I've added water as a neutral species, and so I form that. Okay, and then what's going to happen? Molecule of water is going to come in and take a proton off, pushing those electrons in. How many times have we seen this happen? This is ubiquitous through a lot of mechanisms in organic. Wherever I have a protonated water that's added to something, I'm always going to pull the proton off in the end, right? And the result of that, I'm going to close my brackets. The result of that is I've now deprotonated, so I get the gem diol. But here, pulling this proton off, I formed another H3O plus in my reaction. You know, the catalyst is now regenerated, right? Now notice here, it's different. With base catalysis, I made the nucleophile more nucleophilic. Here, under acidic conditions, the nucleophile is not more nucleophilic. In fact, that's not nucleophilic at all. This is the nucleophile, and it's neutral water. So that it's not that the nucleophile is more nucleophilic. What does it do, though? It makes the carbonyl carbon more electrophilic, because now the oxygen that's attached to it has a positive charge. It's even more electronegative. So my induction through that double bond is increased, and so it enhances the positive charge character of this carbon. So it makes this more electrophilic. Now this is what you call, a really good short answer question on a test. How do the different types of catalysis affect, the nucleophilic addition? Base makes the nucleophile more nucleophilic. Acid makes the carbonyl more electrophilic. So base more nucleophilic, acid more electrophilic, and that's what you would expect, right? Because bases are nucleophiles, acids are electrophiles. Okay, so it's kind of easy to remember that way. All right? And so now, this is kind of the typical way that you'd see any reaction occur, where you have, your nucleophile being something like HY. H attached to some nucleophile. Okay? And the way to think about this, if your Y is electronegative, and those are going to be things like oxygen, sulfur, halide, then Y can support a negative charge. Okay? And so this is not acid versus base catalysis we're talking about anymore. This is actually talking about whether it's reversible or not. Okay? Because I think I said this before, if your Y group here can support a negative charge, then if you look at it in the case of reacting with a ketone or an aldehyde, and let's do HY, and you're going to add that Y, and I'm going to go ahead and draw the product if you do this addition. If your Y can support a minus charge, then that's just basically going to ensure that the reaction is reversible, because this Y can come back off and you're back to where you started. Okay? That doesn't mean that it's necessarily not a good reaction, but it is reversible, which means at equilibrium you're going to have to look at the percentage of this versus this to see if in fact the reaction is favored as written. Okay? And so that's really what governs whether something is reversible or not. So when we go to our very first specific reaction now. Let's keep all that in mind about catalysis and reversibility, because the first thing we're going to talk about is cyanohydrins. Okay? The hydration reaction was just to demonstrate these features. Now we're going into nucleophiles that we add to the ketone or aldehyde, and we actually get legitimate products. So these are where the reactions start, where you're going to have your flashcards. Okay, so the first nucleophile is forming cyanohydrin. So the nucleophile that we're going to react with the ketone or the aldehyde is HCN. Okay, and so the result of the cyanohydrin, as you can imagine, is where I'm adding CN as my nucleophile. So that means when I react with a ketone or aldehyde, I'm going to end up with cyanohydrin, because it has both of these groups geminal to each other. All right, so how's the reaction going to occur? An example of that is, let's say that I have this aldehyde, and I'm going to react it with HCN. Okay. Now, before I start, we'll think about, we'll show it in the mechanism in a moment. But as I'm starting this, I can see that this falls into the HY formula, right? Because CN is a good leaving group. So that means I know this reaction is going to be reversible. However, the equilibrium does lie on the side with products. It lies on the right side as written, and so this reaction occurs and I get the cyanohydrin with the CN has added, and it gives me this product. All right? So mechanistically, how is this happening? Well, let's look. The mechanism is going to answer questions for us. So mechanistically, the reaction is reversible, as we just saw that, because CN minus is a good leaving group, so it can come right back off. So the importance is where the equilibrium lies. Okay, and it's also base catalyzed. So that means that you need, for this reaction to occur, when I'm looking at the mechanism, I have to have CN minus, because base catalysis then makes this more nucleophilic. So it is actually with the minus charge. So that negatively charged nucleophile is going to react with the electrophilic carbon, the carbonyl, breaking the pi bond, moving the electrons out to the air, forming the tetrahedral intermediate, which would look like this. All right, because I've moved my electrons out to the carbonyl oxygen. I have an H attached, and I've added this CN. Okay, I've added it as a negatively charged nucleophile, therefore it has no charge there. Okay, then what happens? I have another molecule of HCN. Okay, this pulls that proton off of the HCN, which protonates that and leads to the alcohol. So I've protonated my O, and then I have my H and my CN. CN is a nucleophile that's added. I've removed that proton, and in the process, I've taken an H off of HCN, so that leaves me with CN minus. And that CN minus then is able to come and react with another aldehyde. Okay, so base catalyzed reaction. And so all that's necessary is you have one molecule of CN minus in the reaction when it starts, and it will proceed. So see, that's how you can see clearly, base catalyzed, reversible. Okay? Now there's a synthetic utility reaction that goes with this. So this reaction is a way of making a cyanohydrin, so getting both CN and an OH present on your molecule. So how can we use this to our advantage in a synthesis problem? So synthetic utility. So let's say that we have done this reaction and we formed decyanohydrin. There are two reactions. One of them we certainly know already, so it's review, and that is we can take this and we can do a reduction using LAH followed by acid workup. Okay, so we've seen these reduced carbonyl compounds, but CN, that cyano group, remember I stated earlier, is its reactivity is related to carbonyls. And so it is in fact reduced by LAH. And when it's reduced, what do you think a CN is going to be reduced to? Because remember, when you're doing reductions in organic chemistry, what that basically means is you're adding H's. So you're basically reducing the CN to CH2NH2. So you're forming an amine functionality. Okay? And there's chemistry that we know how to do or will learn how to do on that product. So that's one way of altering the cyanohydrin into another functionality. The other thing you can do is just a straightforward hydrolysis under acid conditions and heat. And basically what you do is you hydrolyze the CN. When you hydrolyze a CN, you form a carboxylic acid. Okay, so that's a way of converting a CN into a carboxylic acid. Both of these, synthetic utility reactions, they would appear on your flashcard as I've written them, but it's ways of converting this functionality into something else that you could use synthetically. All right, the next nucleophile we want to talk about that would react with a ketone or an aldehyde is a Grignard. Now, who knows what I'm about to say? This is review. We've already talked about this reaction. We're going to see that a lot this semester. I'm going to show you this reaction because it is a nucleophilic addition reaction of ketones and aldehydes. We've already talked about it. We talked about it as a way of preparing alcohols in the last functionality discussion. Total review. And so that is basically you take your ketone or aldehyde and you react it with the Grignard followed by acid workup. And what forms? The alcohol. Okay? Already done this reaction. Don't even really have to discuss it. Okay? We've also talked about the next one. If you have a ketone or aldehyde, you can react it with the hydride nucleophile. This is review. I've already talked about this. Don't really have to spend any time on it. That is, you have a ketone or an aldehyde. You can react it with a hydride reagent. Okay, and the two that we talked about were what? Sodium borohydride or lithium aluminum hydride. And remember, it was always followed by acid workup. And the result was what? The addition, I didn't put a problem, the addition of the H as a nucleophile, so you end up with an alcohol. Okay? This was a standard reduction reaction, but hydride is a nucleophile reacting with this. Now, there are two things that we didn't do on the last one. Okay? These reactions are not reversible. The Grignard and the hydride, the ones we've already talked about, they're not reversible. Why? Because an R minus and an H minus aren't good leading groups. So they're not reversible. Once they add, they've added. And they fall under the category of basic because they are actually, R minus in reactivity and H minus. So it's the nucleophile is more nucleophilic. Okay? So that's true of both of those reviews. Okay? And that brings us to the next nucleophile, which are amines. Okay, and what we're going to talk about now, amines, this is the first case of a neutral nucleophile reacting with the ketone or the aldehyde. Remember when we made that chart at the beginning, when we made our list, and I pointed out that amines were the main neutral nucleophiles we're going to talk about because the amine is nucleophilic enough without being, without any kind of basic catalysis. It's also nucleophilic enough to react with the carbonyl without it being protonated to make it more electrophilic. So amines will react with ketones and aldehydes without any assistance. And so that makes their reaction a little different. And what we're going to form is either imines or enamines. Imines or enamines. Two different functionalities that we haven't looked at before, but they are the result of the addition of an amine to a ketone or aldehyde. And we're going to see what those structures look like. So if I have a ketone or an aldehyde, and I'm going to draw it in a particular way to emphasize something. So say those are R groups. So here is a ketone, and I can react it with, and by the way, as you can see right away, these reactions we're going to look about are reversible because the amine can easily go on and come back off. Okay? But there are two different things we have to look at. If we have a primary amine, where it's NH2, it's going to have different reaction than if it's a secondary amine. Okay? So we have to divide those into different categories. And mechanistically, we're going to explain what happens in the difference. But the result is, remember, when neutral nucleophiles reacted with a ketone or aldehyde, we saw this, last lecture, they expel water after they add. And so you end up with, instead of a carbonyl going to an alcohol, you end up with whatever the nucleophile was, is basically replacing the carbonyl oxygen in the product. And so you would end up with this as your product, and plus water, because remember, water was expelled. And so this is an imine. Imine functionality is where you have a carbon doubly bound to a nitrogen. It's called an imine. Okay? And then what we're going to see later too is if it's a secondary amine that you react this with, you're going to get, you still expel something, but not in the same way. You're going to end up with this structure, where now it's not a double bond, this nucleophile replacing the carbonyl oxygen when the water is expelled. You're actually going to end up with the double bond between two carbons. What was the carbonyl carbon and what is in the alpha position. Okay? And this is called an I want to make sure, enamine. And it's not, you don't say enamine, even though it probably would make more sense, enamine. This is because it's got a double bond. Okay, and it's an amine. Okay, so these are the two functionalities that occur when you add this neutral amine to the ketone or the aldehyde, and you expel water in the simple case over here to get the amine. You get an elimination over here to get the enamine. So two different products. So the question we need to look at is, why do we get two different products using primary or secondary amines? And so that's going to fall under, well, what is going to explain that for us? Right, the mechanism. Okay? And so we're kind of at that point where I want to do kind of foreshadowing, because I want to be able to go completely through imine formation and enamine formation in one sitting. I don't want to split it between lectures. Okay? And so I'm just going to kind of do some foreshadowing when you have your imine formation, you're going to have a reaction that we said is reversible, okay? And it's going to be acid catalyzed, but not in the way that we talked about before. You're going to see, because as I said, it doesn't involve any catalysis for the initial reaction. The acid catalysis comes in later, as we're going to see. But what we're going to work through is exactly what happens when this neutral amine reacts with that electrophilic carbon of the carbonyl, breaking the pi bond, moving electrons onto the O, forming the tetrahedral intermediate. So you're going to see we're going to have a little different thing that's going to form, because we are going to get, put my two R groups like that, we are going to get the normal tetrahedral intermediate with the minus charge on our oxygen because we've moved the electrons up there. But now we have this neutral amine that has added, right? And so it's going to look like this. It's going to have a plus charge on it. And so there are going to be some different things that happen, because we're going to have a proton transfer here. This proton is going to be transferred to here. And then we're going to look next time on exactly what happens. So I'm going to start right here, and we're going to look at how water is expelled from this to give us the imine product. And we're also going to talk about how this acid catalysis comes into play. And then once we finish that, we're going to go back and do the mechanism where this, instead of being the primary amine, where it's a secondary amine, and how that affects the reaction towards the end. All right, so I will see you next lecture.